All right, we have this system. K1, K2. We're going to get different Ks now. And mass 1, mass 2. Let's just say M1 equals 9 kilograms. M2 is equal to 1 kilogram. K1 equal to 24 newtons per meter. And K2 is equal to 3 newtons per meter. And then we have some initial conditions, right? Everybody needs initial conditions. X10 is equal to 1 millimeter. Let's go. V10 is equal to 0 millimeters per second. X20 is equal to 0 millimeters, and V20 is equal to 0 millimeters per second. All right, so calculate the natural frequencies and mode shapes using the eigenvalue solution, right? So how hard can it be? Pretty easy, right? Like, I don't know, like us beating Clemson in football. Super easy. We got this. All right. M is equal to 9001. How about that? Nice diagonal mass matrix. What we like. K is equal to 27, -3, -3, and 3. And you can solve through those at your leisure, but that's just what that equals. All right, we need our mass normalized stiffness matrix. So K tilde is equal to M -1/2 K M -1/2. And K M -1/2 equals 27 -3 -3 3. And then I'm going to have 1/3 0 0 1, and that's going to be 9 -3 -1 3. I admit that I could have you could do this all in one line, but you want to do the first. You want to do the K M to the -1/2 to kind of maintain symmetry, and also it's just easier to break it up, right? Instead of doing it all in once, and people ask which one you did first. So, and now I can. So now that I have that, I can get that K tilde is equal to M to the -1/2, which is 1/3 0 0 1. Times Km to the -1/2. Well, I've already solved that. So it's 9 -3 -1 3. So hopefully that makes sense, right? I just broke it up. Instead of 3 matrices, I just did it twice for 2 matrices each. But it's the same thing. So that gets me a mass normalized stiffness matrix of 3 -1 -1 3. All right, so now I need the solution. I need to solve k tilde, which I have matrix of eigenvectors is equal to my eigenvalues, which is technically a vector of eigenvalues, v. So we can use a computer to solve that. Anyone remember how to solve an eigenvector of a 2x2 matrix? Yep. So first, to solve a 2x2 matrix, and you'll this might be a exam thing, so make sure you know how to do this. We can rearrange this as k delta minus lambda I v is equal to 0. And now I take the determinant set equal to 0. So my eigenvalue cannot be equal. My matrix of eigenvalues can't be equal to 0, right? That would be problematic. And so this must equal 0. Or the determinant of that must equal 0, which gets me one value. So my determinant of 3 minus lambda negative 1, 3 minus lambda, negative 1, must equal to 0. Remember, A times D minus B times C gets us a characteristic equation that looks like lambda squared minus 6 lambda plus 8 is equal to 0. How do we solve a characteristic equation, right? We need to find the roots. So the roots of this are the eigenvalues, and so we can get lambda 1 is equal to 2, because that'll get me 4 minus 12 plus 8 equals 0, and lambda 2 is equal to 4. That will also get me 0. Okay, so those are lambdas. So then what are my natural frequencies? What are the natural frequencies?
2 and squared.
Perfect. So omega 1 is equal to the square root of 2. And omega 2 is equal to the square root of 4, which just equals 2. How's that sound? So I was able to obtain my natural frequencies by solving for my eigenvalues. Now I need to solve for my eigenvectors, right, to get my mode shapes. Yes.
So is omega 1 and omega 2 related to the individual masses for natural frequency? No? Okay.
So omega 1 is the first natural frequency of the system, and omega 2 is the second natural frequency of the system.
Okay.
And each mass oscillates at a combination of the two masses.
Okay. So like omega 1 would be the first mode shape, and omega 2 is the second mode shape? Or?
Omega 1 would be the frequency that the first mode shape oscillates at.
Okay.
And omega 2 would be the frequency that the second mode shape oscillates at. So if you think of this bridge, quite dangerous, as a 2-degree of freedom system, right? You have a bunch of first degrees of freedom here, you have a bunch of second degrees of freedom here, but every segment of that bridge oscillates at a combination of the first and the second modes, because they are coupled ordinary differential equations. That's the coupled part, and they're coupled through the, that is definitely a question on the final. They are coupled through the What is the term that couples our two equations? What? Yeah, what is the term that we added that couples the two ODEs? What have we added to multiple degrees of freedom that we've never seen before? Mode shapes. The mode shapes couple your system of ODEs. Let's go back to that. That's very important. There's a combination of things here that are important. Equations are coupled through your mode shapes. These are your two equations. Each one of those equations is true, and they give you the x of 1, which is the displacement of mass 1, right? And the mass 1 vibrates at some amplitude of the first natural frequency plus some amplitude of your second natural frequency. And those amplitudes are related to our participation factors, which is what we've been calling Q. Did that help clear up some things? But make sure that you understand that the equations of motion, your two equations of motion, you have a system of ODEs. And they are coupled through your mode shapes, and because you have a mode shape that appears in both. Does that make sense? Great question. It's a hard concept. Like I'm not trying to pretend like this is easy. Just look at the math. Okay. It's not quantum algorithms, but it's pretty close. All right, solved our eigenvalues. What's the next thing we want? Vectors. Vectors, and what do vectors give us? Mode shapes. Mode shapes, right? So, solve for eigenvectors. Well, that's easy-ish. K tilde minus lambda 1 times I is equal to 0. This is going to give me my first mode shape. Why will it give me my first mode shape? Because what? Yeah, because I put my first eigenvector in. If I put my second eigenvector in, what do I get? Second mode shape. Perfect. So K tilde minus lambda I, that's pretty easy.
We're setting lambda 1 equal the smallest eigenvalue, right?
Yeah. Yep. That is how I would always do it. Just remember that not every software package, I think the software packages you use will, but not every software package will organize them smallest to largest. In structural dynamics, we definitely want them ordered that way. In mathematics, it means nothing. So that's not a concept that that eigenvalues need to be ordered from smallest to largest, but we like it in engineering. So you're going to end up with 3 minus 2 minus 1 minus 1, 3 minus 2. Sorry, I was missing something here. Got to have that V. And then you have a V11 and a V21 is equal to 0. I guess we should make, I mean, that's technically correct, but we can write it as a matrix of zeros. 0, 0. Same thing. All right, we have two dependent scalar expressions, right? We have V11 is equal, oops, sorry, minus V21 is equal to 0, and we have minus V11. It's going to be plus, right? Plus V21 is equal to 0. All right, so we want to make sure that these are normalized, right? So let's apply a scalar a to normalize it to a unit vector. How do I want to write this out? So maybe another way to think about this is, probably a better way to think about this is, so V11 equals V21. Do you see that? If I just move it to the other side, V11 equals V21. So we want to normalize this. So let's apply a scalar. So we get a normalized vector, right? Because if you think about it, let's just say that I applied, let's just say I drew this out and that each was equal to 1. So if I'm 1 here and I'm 1 here, my vector between the two, right, is definitely not going to be a length of 1. So let's go ahead and normalize that out. So trying to find our alpha value for the normalization, alpha of 1, 1, alpha of 1, 1 is equal to alpha squared of 2, which is equal to 1. I move my 2 over, I take the square root, and so page so then I can get, that became an A somehow, so I can get alpha is equal to 1 over the square root of 2. That allows us to normalize the vector. So now we can normalize it. Now we can normalize the vector as alpha v1 is equal to 1, right? So drawing that out, we get alpha of v1 is equal to 1 over the square root of 2 times 1, 1, which is what we solve for, but we just want a unit norm of a vector, which is equal to 0.71, 0.71. That is our mode shape for our, sorry, that is not our mode shape. It's tricky. That is our eigenvector. That is our normalized eigenvector for 1, 1. We can follow a very similar process now. So redo for lambda 2 is equal to 4, right? And that leads us to alpha v2 is equal to 1 over the square root of 2, 1, 1 is equal to negative 0.71, 0.71. And again, we normalize for a couple of reasons. One, it's just always nice to work in normalized vectors. That's probably the biggest deal, right? And when you actually do it in code, it's not hard, you know. But we want these normalized vectors, so everything's always going to line up. Okay. Lastly, the normalized eigenvectors, right, can now be converted to mode shapes, right? Because if we didn't have a normalized vector, we would have to adjust our mode shape to match, and that gets quite hard. So we have to normalize our vectors, and that can be converted to a mode shape. U, that's a bold U, right? So the matrix U is made up of my two eigenvector, of my two mode vectors. So let's just say that equals to U vector 1, U vector 2. That makes sense? That's my bold mode shape. I'm going to write it as U is equal to M negative 1/2, that's my mass normalization, times my vectors, my normalized vectors, right? We can do that complete, or we can break it out. Let's say for this example, let's just break it out. And then let's give you U1 vector is equal to 1/3 0, 0, 1, 0.71, 0.71 equals a 0.24, 0.71. And U2 vector is equal to 1/3 0, 0, 1, negative 1, 1, which is equal to negative 0.24, 0.71.
That's supposed to be negative 0.71, 0.71. Or usually, like where you're multiplying by negative 1, negative 1.
What do you think it should be?
Negative 0.71, 0.71.
For the second one?
For U2, like the 1/3 0, 0, 1 times negative 0.71, 0.71 equals negative 0.24, 0.271.
Oh, instead of negative 1 and 1?
Yeah.
Yeah, that's correct. Thank you. That's negative 0.71, 0.71, like that, right? Yeah, those, I'll update those in the notes. Okay, so this, again, these are our mode shapes. Now, everyone's favorite thing, what do we want to do to these mode shapes? Do we want to report them as 0.24.71? No, we want one of those values to be 1, right? So we renormalize. Back to 1, right? Again, mode shapes are just shapes, and so when you plot them, we want one value of the mode shape to be renormalized back to 1, and then we do that again here. But you have to normalize as you go through also, so you get the correct value